Hello everyone. Now we are going to cover the main important non-dimensional numbers for the external convection problem. So we will first cover the Prandtl number. So what is Prandtl number and its importance? So Prandtl number shows the ratio of the kinematic viscosity over thermal diffusivity, and the kinematic viscosity is the ratio over the ratio of the dynamic viscosity over density, and the kinematic viscosity is the K by rho Cp, which is conductivity, density, and the specific volume. For the definition of the kinematic viscosity, we have a separate video that shows its importance, and for the definition of the alpha, which is the kinematic viscosity, it shows the ratio of the conductivity of the material, how material conducts heat versus how it stores the heat. Okay, so its thermal storage capability, which is rho Cp, and the K is its conductivity capability. Okay, it shows this ratio, and these two ratio gives us the Prandtl number. So now the importance of the Prandtl number. So we'll look for two cases where Prandtl number is less than 1 and where Prandtl number is much greater than 1. Okay. When Prandtl number is less than 1, it means that mu by alpha is much less than 1, and it is the case for the non-viscous, or we can say the inviscid and conductive material. So this is the case for inviscid conductive material or fluids, we can say it. And now we will show what it means when the Prandtl number is less than 1. This is the flat surface, which is the famous and the easiest external convection problem, and the flat surface is hot, Ts. Okay, and if the Prandtl number is much less than 1, then it means that the viscosity of the fluid is very low, therefore it is inviscid. If the viscosity of the fluid is very low, then you will have, so if this is apart from the fluid, if the viscosity is very low, here you will have the no slip boundary condition. But since the viscosity is low, this viscosity cannot affect most of the fluid domain. It only affects a small part over here. Okay. And the rest will be U infinity. So here U infinity, until this part it is U infinity. And you have only this small region where mu affects. Okay. Because mu by rho is very small, it means that mu value is very small and it affects only a small part in the fluid domain. But on the other hand, it is a conductive material. Conductive material means that the K is too high. So K by rho Cp, and here K value is too high. And we know that for laminar boundary layer, the fluid doesn't have any velocity in y direction. So it is y direction, and this one is the x direction, and the Vy is equal to 0, and therefore heat transfer in y direction is only dominated by conductive heat transfer, and so you will have a profile something like this one, because the K value is too high, and then you will have a profile something like this one. Okay. And you will reach T infinity somewhere around here. So this one is the T infinity, and till that T infinity point you will have the boundary layer. Okay, this is the thickness of the boundary layer for the thermal boundary layer. This one is the thermal, but the velocity boundary layer, it is very small. This one is the velocity boundary layer, delta velocity. And if you look at the Prandtl number much greater than 1, what you will have here is that again we have the flat plate which is very hot, and in this case you will have mu by alpha much greater than 1. If it is much greater than 1, it means that it is highly viscous but non-conductive. And you will have exactly the opposite of this case. So you will have the high or thicker boundary layer, so it will be something like this one for the velocity. You will reach U infinity somewhere around here. It will be U infinity, and this is the thickness of the velocity boundary layer. Okay. and the boundary layer for the velocity, this one will be the thicker. Okay. But if you look at the thermal boundary layer, you will have something like this one. Now the alpha is small. Alpha small means the conductivity is small, and we know that in y direction velocity is 0. It is transferred only by conductivity, and therefore this conduction heat transfer only affects a small layer here, and the rest is T infinity. This part is T infinity, and this is the thickness of the thermal boundary layer, and this one is thinner. Okay. This is the first important of the Prandtl number, and for Prandtl number much greater than, we have the glycerin, engine oil. Okay. Prandtl number less than 1, we have the liquid metals. Okay, these have the Prandtl number much less than 1. Okay, so if you go back to the slide, so you have Prandtl number much less than, for example, mercury. Okay, so it is liquid metal and it has very low Prandtl number. So it means that it is not viscous, but it has high thermal diffusivity. But on the other hand, glycerin, you can see the high Prandtl number value. Good. This is the first importance of the Prandtl number. Second importance of the Prandtl number is that if the Prandtl number is low, we have, so if you go, this is your pipe. If Prandtl number is much less than 1, we have said viscosity is small. If the viscosity is small, then the boundary layer grows at a very low speed. Okay. If it grows at a very low speed, then this will be the thermal velocity entry length. Velocity entry length. Okay. Since the mu is very small, then you have the entry length which is very long. Okay, this one is long. But the K value is very high. If the K value is very high, then you will have the thermal entry length which is short. Okay, this one is short thermal entry length. Okay. What it means that if the entry length is if it is long, it means that we need higher pump, because longer velocity length means that higher F value. Higher F value means higher pressure drop, and the higher pressure drop means that you need more powerful pump. Okay, so it is a result of the power. And the short thermal length means the H value is high. If the H value is high, then it means that it is, K value. K value is high. It means that you have good conduction here. Okay, the good heat transfer by conduction. Okay, it is not about convection. Okay, it is about the conduction. K. Good. Now let's see the opposite case. And for the opposite case, again, we will have the pipe here, and you will have now longer thermal entry lengths because the K value is too high. This one is the thermal entry length, and the velocity entry length, this will be very small. This one is the velocity, this part actually, so let me erase it and put it up again. And now you will have the velocity entry length. This one is shorter velocity entry length. Yeah. And we know that mu is very similar to, K. Okay, so mu distributes momentum in y direction, and the K also distributes the heat in y direction. Okay, and this one is dominated by K, and this one is dominated by mu. Okay, so they have the similar properties. This one distributes momentum in y direction, and the K distributes heat transfer in y direction. Okay, but they are all distributing x direction values in y direction. Okay, this is the importance of the Prandtl number. Now we will talk about, we have a simple question here. It says that we have the copper with a higher thermal diffusivity than aluminium. Which material would you select for cooking food? Okay, say that we have a pan like this one, and you are trying to cook the food inside, and the one case is the aluminium and the other case will be the copper. So if you are transferring heat from below, and then you will have K by rho Cp. For the aluminium, it says that it has lower thermal diffusivity. If it is lower, then it means that the rho Cp of aluminium is high. Okay. And if it is high, it means that the aluminium, so we know that Q dot stored will be equal to m dot Cp delta T. Okay, so in this case, Q stored will be mCp delta T by delta T. Okay, Q dot stored, because this one is for open systems. Now in this case, it is closed. Okay, and then if Cp is high, if rho is high, mass is rho into volume, it means that the temperature change is very small for the same heat transfer. If the temperature change is small, it means that the material doesn't, so here you have T2 and here you have T1. If the difference between T2 and the T1 is small, and then it means that the food is not getting good amount of heat. But for the copper, T2 is much greater than T1 because it has lower rho Cp, and lower rho Cp means higher delta T, and the higher delta T means that T2 is much higher than T1, and therefore the food feels the temperature much better than in the case of the aluminium. Therefore we should select the copper. But if it is cost, then aluminium is better because aluminium is cheaper. Okay, another non-dimensional fluid, non-dimensional heat transfer number is the Fourier number, which is very famous, and the Fourier number compares two times. So you have one time here, so this one is time 1, and this one is another time, L squared by alpha. Okay, so for the Fourier number, what it says that this is the process time. Okay, the process time, it can be that you are heating, there is a sample here, and you are heating that sample with some Q dot. And let's say that you have heated for 5 seconds. Okay, and for this 5 seconds, what will happen is that the sample will feel a different temperature here, which is T2, and if the sample has the temperature of the T1. Okay, this T2 temperature will propagate through the sample at some speed. Okay, and until this end. So you will have the thermal wave. Okay, this thermal wave has some speed, and that speed is proportional to thermal diffusivity of the material, how it conducts heat versus how it stores heat. So higher alpha, and it means that the shorter time for the travel, and as well as the smaller the length of the material, then it means that the shorter time to travel. Therefore, what we are doing is that we are comparing the time for heating versus the time required for the thermal wave to travel from one part of the material to the other part of the material. Okay. These two time ratio gives us the Fourier number, which is non-dimensional number. Okay. L squared by alpha is the time required for thermal wave to propagate into the domain from one part to another part by thermal diffusivity, and the other one is the time required for the process to happen. And the one thing we should note it here is that, so when you are heating the material, we should note it here, so when you are heating Q dot in, okay, so let's say that this one is 150 kilojoules. Okay, some of this Q dot is stored. Okay, so let's say that some of it is stored, Q dot stored, and that is proportional to rho into Cp. Say that 50 kilowatts, this one is watt. And the sum of the heat will be conducted, Q dot Cd, and the difference will be 100 kilowatts. Okay. So this one is proportional to K, and this one is proportional to rho into Cp. And the ratio here, how much is transferred, how much is stored, and determines the diffusivity of the material, which is the Fourier number. Okay, another heat transfer number is the Nusselt number. Okay, and what Nusselt number is doing, Nusselt number is equal to the H, L characteristic divided by K, and this is the Nusselt number. And what it does is that it compares the convective ability of the fluid, convective ability of fluid versus it is conductive. Okay, So if HL bar K is large, it means that the fluid convects much better than it conducts. So if I give a simple example here, okay, so this part is the infinity value that you have reached. This one is the infinity value. Until that part you have the gradient. Okay, so this thickness delta T, let me write it here. This delta T, delta thermal, it is only determined by the conduction. Why it is determined by conduction? Because velocity in y direction is 0. If the velocity in y direction is 0, it means that q dot transferred in y direction is proportional to conductivity only. And we know that from the conductivity formula that K into A into here you will have the temperature at Ts, and here you have the temperature at T infinity. It will be Ts minus T infinity by delta T. Okay, and we can write this one as, so if K by delta T into A into Ts minus T infinity. Okay, and if I write the formula for the convection, it is HA. So here the A's are same, because if you take an area like this one, it is the same area for conduction and the same area for convection. Okay, and then you have Ts minus T infinity. Okay, and here from that part to this part, convection is equal to conduction, because here we don't have any advection, therefore they are purely equal to each other. Okay, and since no advection, okay, since no advection, it means that HA delta T is same as KA delta T by, okay, this one delta T small, and then this one cancels out, A cancels out, and the H is K by delta T. Okay, if I replace back to here, so Nusselt number will be equal to L characteristic by delta T. Okay, and you can see here that Nusselt number is the ratio of the length. But it says that it is the ratio of the how fluid transfers convection, the distance that convection is transferred over the distance that the conduction is transferred. The ratio of the distance, this one is for convective length. Okay. For flat plate, convective length for flat plate, it is L or X variable. So if I take this L, this is the L that is fully heat is transferred. For X direction, heat is only transferred by convection. This convection. Why it is convection? Because we have Vx, which is not equal to 0. Okay, and then this compares the distance that convection heat transfer occurs over the distance that the conduction heat transfer occurs. And for this length, you will find the average distance for the thermal boundary layer, which is determined by integral, and then you can find the ratio, and that gives you the Nusselt number. These are same stuff. Okay, this is the definition of the Nusselt number, and we have the last number, which is important for fluid heat transfer problems, is that Biot number. Biot number shows the ratio of the resistance that you want to neglect and the resistance that you consider it is dominant. Okay, we will give two examples. One will be the lumped capacitance example, the other one will be the fin example. And for the fin, we have a symmetry about the x-axis. This is the x-axis and this is the y-axis. Heat is transferred symmetrically about the x-axis, and this is the width, and this is the length, and this is the thickness, and over it we have the convection. And what we are saying is that for fins, the fin problems are one-dimensional. One-dimensional, we mean that q dot y is 0. Q dot y is approximately, let's say that 0 for CD. Therefore 1D fins. Okay, we want to prove that it is actually true. What we will do that if you neglect the resistance, then Biot number should be less than 0.1. Okay, so let's compare the resistance in y direction, and we should compare the resistance that we think it is important. For our case, we say that it is important for CV. Okay, we say that convection resistance is much more important than the conduction resistance in y direction. Okay, and let's now compare it. Resistance in y direction due to conduction. So conduction resistance in y direction, I'm going to take one part. So this one is Q dot CD. This one is actually, let me erase it. This one should be. Okay, we will only consider one dimension. So one part of the fin, which is the symmetric part, other part is symmetric, QCD Y. Okay, it only happens in Y direction. And the resistance in Y direction is the thickness of the fin divided by 2. So this is L by K into A, and the L is delta, here it is T, is T by 2 divided by K into the area that heat is transferred, and this area is W, this is the area that the heat is transferred, W into L. W into L. And we say that this is much smaller than the resistance for convection. We assume it, okay, we will prove it now. So RCV is 1 by H into A. Okay, 1 by H. For CV heat transfer, we have this area, okay, the surface area over here, which is W into L again. W into L again, because we are considering this part only. You can consider the front and the back surfaces, okay, it depends, but we are considering only this for area, and this one will be 1 by H into W into L. So if you compare these two values, RCD by RCV, and this will have the thickness by 2 divided by K into W into L and multiplied with H into W into L. Okay, this one cancels out, and you will have H into thickness into 2K. Okay. And if you want to be valid for one dimension analysis for the fin, then it should be smaller than and equal to 0.1. And the H and the K values, you cannot change these values, and therefore you can play with the thickness values. And most of the time, thicknesses of the fins are on the order of 10 to the negative 3. Okay. Therefore, this approximation is the valid approximation for fins. And now we'll do the same case for the lumped capacitance method that we have covered in our lectures. Lumped capacitance. Okay. And here now we'll compare RCD for the lumped capacitance method for RCV, because we are saying that CD resistance inside the material is very small with respect to CV resistance around it. Therefore, we are thinking that it is zero-dimensional problem for the material itself. Okay. So for the CD, for material, you will have again RCD will be equal to L by K into L, A. Okay. For this lumped capacitance method, we are taking L as volume by surface area. Okay. And if you write it, you will have, so volume by surface area, volume of the sphere is pi d to the power of 3 divided by 6, and the surface area is pi d square. And if you divide it, volume by AS will be the L, and that one will be equal to diameter by 6. Okay. And the K into area. Area is the surface area. We can write it as surface area. And the CV is again 1 by H into surface area. They have the same area because here you have the same convection around it, and conduction leaves the material through the surface area. If you divide it, you will have RCD by RCV, and that one will be equal to surface areas cancel out, and you will have H by K in the diameter by 6. Again, you should have this value smaller than 0.1 for the lumped capacitance method to be valid. Okay, same as here for the fins, it should be much less than 0. It should be less than 0.1 or equal to 0.1. So we have covered the non-dimensional numbers in heat transfer. So Nusselt number, Fourier number. Okay, and the last part says that it express exponential function for the lumped capacitance temperature change as product of the Biot number and Biot number and the Fourier number. So I can write it as Ts is equal to Ts initial minus T infinity e to the power of HAS by mCV into T and the plus T infinity. This is the temperature versus time. And now I can write it as HAS by mCV into T, and I know that Biot number is HL characteristic, and we said that L characteristic is volume by AS and divided by the K value. Okay, this was the Biot number. So I can generate Biot number from here. What can I do? Is that H, and instead of M I can write rho into V. Yeah, so you will have H AS into rho into V into CV into T. We have the H, we can find now volume by AS. So what can I do now is that, so volume by AS, so it will be, this one is L characteristic. So I can write L characteristic and divide and multiply with L characteristic, and then you will get the Biot number from here. So I do that, so L characteristic into H into divided by K. So I will do that for the K now. So I will multiply and divide with K. So then you will have H, L characteristic, and the K. This one is the Biot number. And then you will have the rest as this one will be equal to Biot number multiplied with T into K into divided by L characteristic, rho CV, and the AS, we can bring it to downstairs, it will be volume by AS. And this one is L characteristic again. So this one will be equal to Biot number into the time into K divided by L characteristic squared rho CV. Okay. And rho CV by K. So if you go back to here, so we have the CV by K, okay, and this one is exactly K rho CV by K, and this one is alpha, okay, and you will get Biot into alpha T by L characteristic squared. Go back to here, Biot is alpha T by L squared, it is Fourier number exactly, Biot into Fourier number. So I can write this one as Biot into Fourier number, time was included, Biot into Fourier number. So it will be Ts initial minus T infinity e to the power of negative Biot Fourier number plus T infinity. Okay, that's what we are doing for the lumped capacitance method.